Okay, thank you. I'm Spencer, and I'll be presenting our recent submission to Neurips, which is on hippocampal coding as it pertains to contextual capacity and high spatial resolution. So just as a bit of background for those who aren't familiar with what place cells are, they're a cell type found in the hippocampus, and in particular CA1 and CA3, and they're characterized by these single region firing fields. So if you have a rodent traversing a one-dimensional environment, then the first cell might fire in this example here in the pink dots, and then the second cell the yellow dots, but they're completely spatially localized. What we were interested in our work is that if you take a rodent and you move it from an environment A to an environment B, the population level tuning of your place cells totally remaps. And you can also have place cells in 2 dimensions. But this is independent of correlations between your environment, which is a little bit surprising because you might expect that your coding for different environments is based off the correlations. But this is not the case. So we were interested in what kind of global information you could take from this global remapping, and we, in our paper, found three of these things. The first was that you could store potentially very many contexts with a coding strategy with remapping. The second was that there's a fundamental trade-off between your spatial resolution and this contextual coding capacity. And finally, we are also looking at an optimal bias for place fields away from the center of an environment. So just to give a picture as to how we view these things, if we look at the population level tuning of a bunch of place cells, we can view this as an embedding into the high dimensional space of firing rates of neurons. So if you have 100 neurons, then this space is 100 dimensional. And for each position in your room, if the neurons are not noisy, then the rate maps that you get for each position will be unique. And of course, you can do this in 2 dimensions or 3 dimensions. But in any case, you'll get a low-dimensional structure which reflects your environment encoded in the high-dimensional space. And if you have 2 environments, then you'll get 2 structures. And because the dimension of the space is so high, these 2 structures will likely not intersect. But of course, neurons are not noiseless. They are quite noisy. And so we're interested in seeing if we can distinguish which context we're in just from firing rates in the presence of noise from hippocampal codes. And we can use this to characterize whether these 2 contexts are separable. So for a picture of this, you can view these 2 low-dimensional structures. If your neurons are too noisy, or these structures are too close together, then your noise could kick you from one of these neural manifolds onto the other. So to characterize if two of these environments are separable in code space, we want the distance between their rate manifolds to be greater than some characteristic distance set by noise. And in our paper, we consider 2 noise models. The first is a very simple Gaussian noise model, where each neuron has constant noise. The second is still Gaussian, but it's a bit more realistic in that we have a firing rate variability which scales with the firing rate of the neuron. And this is supposed to mimic like an underlying Poisson process for spike generation. In this talk, I'll mostly focus on the first, but all of the intuition sort of follows for the second. So if we're just interested in seeing if we can separate 2 contexts, then we can view this in one of 2 ways. You can either view the noise as giving each of these manifolds sort of a characteristic width, or for the simpler noise model, we can just require that the distance of closest approach of these neuronal manifolds is greater than this distance set by noise. Of course, we're interested in doing this for more than 2 particular rooms. We're interested in doing this for any 2 rooms that you might hand me. So we use gamma Poisson statistics, which are known from experiments to generate rooms, and we're interested in the probability that any 2 rooms generated with these statistics are separable under these type of noise conditions. And asymptotically, this minimum distance distribution is Gaussian, and so we can characterize this. And we have similar statements for the Poisson-like model. So we're also interested in storing more than 2 rooms. So we might be interested in the probability that M contexts are distinguishable, or N environments are distinguishable just from their rate codes. And this is union bounded above by the probability that from any of the M contexts that you choose, 2 of them are distinguishable, which is just this probability that 2 are distinguishable raised to the M choose 2 power. And we can invert this to get an approximation on the number of contexts you can store given N neurons. And if you do this inversion and make some approximations, this comes out to be approximately exponential. But these constants, A and gamma, they depend on a lot of things. They depend on like the noise, how noisy you assume your neurons are. They depend on the firing field widths of your neurons, and the room geometries, how many dimensions you're in. But what's interesting is if you optimize for storing many, many contexts, this drives your firing field widths to be really, really large. And this is interesting because usually you would assume you want really narrow firing fields for high spatial resolution. So you might get that these two sort of objectives are in tension with each other. So just to characterize the spatial resolution, if you have an estimator of your position recreated from your firing rates, which I've called x hat here, you want this to mimic closely your true position. We avoid any particular choice of estimator by invoking a Kramer-Rao bound. And just as a picture as to what this is based off the Fisher information between your firing rates and your position on space. And this we can calculate for both noise models rather easily. But just for an intuition, if your neurons don't, if the derivative of your like rate maps is 0 everywhere, so your firing rates don't change over space, then you'll have very low spatial resolution. So this will drive your firing fields to be quite small, which means that, like I said before, you have two objectives that are in tension. You have a high spatial resolution, which is the second term, characterized by the Kramer-Rao bound, and then you have this first term, which characterizes the number of contexts you can store, or the probability two contexts are distinguishable, based off of your number of neurons and your width. So we can design an objective function with this weight lambda, which sort of takes you from one of these objectives to the other. And what we see is that if you optimize for the width for this objective function, you get really wide fields if you optimize for storing many, many contexts, but you get really narrow fields if you optimize for high spatial resolution. And why this is interesting is if you look at experiments involving rodents, they do have a wide variety of firing field widths along the ventral dorsal axis, with the ventral cells typically having really wide tunings and the dorsal cells having really narrow tunings. And if you perform lesion experiments on the hippocampus on the ventral part, you lose contextual fear responses in rodents, but if you perform lesions on the dorsal part of the hippocampus, you end up losing high performance on like water maze tasks. So this experimental evidence sort of suggests the stratification of function, and we're suggesting that this is actually purely dependent on the firing field width. So the last thing we were also interested in exploring is biasing place fields towards boundaries, and the reason for this is in our model, if you don't do any bias towards boundaries and you assume your place fields are uniformly distributed over space, you get fewer overlaps near the boundaries, and so where you're most likely to get confused is near the boundaries. So plotted here is if you have two one-dimensional rooms and you're looking at the distance between them in the rate space, you can see this distance is smallest near the boundaries, and where this distance is small, where you're most likely to be confused between these two two environments. And so to counteract this, we can use a non-uniform distribution for place cell distributions, and we use a symmetric beta function for this, and we use this parameter alpha to characterize the uniformity, so alpha equals 1 would be what we were doing before, and alpha equals 0 would basically be two delta functions at the boundaries. So to get a picture as to how we can view this optimal bias, if we take an average over many, many environments, XA and XB, so that we get these smooth profiles for this distance and rate space as a function of position in our two rooms, we get these sort of table-like shapes, and you can see, like I said before, that where you're most likely to get confused is where this distance is small, which occurs near the boundaries of your environments A and B. But as we increase this bias, this minimum jumps discontinuously from the boundary to the bulk. And this means we can calculate the optimal bias by seeing where this first derivative doesn't exist here. And this will depend on both the noise model under consideration, whether we're interested in Gaussian or Poisson noise, and it also depends on firing field width. So we might predict that this bias also changes as you move along the ventral dorsal axis of the hippocampus. So all of this is shown in one dimension for one-dimensional environments, but the analysis in 2 dimensions separates, and it does in higher dimensions too, so you get the same results. So just to recap over the main points, we sort of find 3 things once we view the manifolds in rate space. And the first is that we can store exponentially many rooms. It's a first-order approximation. We also find this trade-off between 2 objectives, and we also find that clustering near boundaries is quite beneficial for storing many contexts. One thing I should mention for this last point is we consider hippocampal coding in isolation, but there are border cells in the medial entorhinal cortex, so you might expect that interactions with the MEC actually decrease the need for such great biases. And also rodents typically explore near boundaries of an environment, so you might get additional spatial biases from that. So some of the future directions we're interested in is considering interactions with these brain regions. Also, this is all done without any regards to the network that might implement these things, which will constrain you a lot further than I've described here. So we're interested also in a few more exact calculations and simple decodability. And if you want to talk more, have a poster later today, and then we have another poster out of our lab on Friday as well. So yeah, I guess that was really quick. So,
yeah, great. We have a lot of, thanks our speaker. Great, we have some extra time for Q&A. So yeah, please line up at the microphones. We'll start over here first.
Thanks so much, great work. I really appreciate the analysis of field width.
Yeah.
I'm wondering if the I thought you were going to go and say that the remapping also helps with distinguishing context. Can you comment on that?
Yeah, so the remapping is, I construct 2 environments using known statistics, but I assume they're independent, which for experiments involving global remapping they are. There's a lot more of other kinds of remapping, like there's rate and partial remapping, which we don't really consider here. But we don't really analyze the mechanism which induces remapping. We just analyze, assuming they have remapped and your 2 environments have independence aside from spurious correlations due to random effects. How separable you might expect them to be. Does that answer the question? Okay, yeah.
Okay, let's go over here.
Thank you for the presentation. It made me feel insecure about my understanding of math. And that being said, you talked about place cells.
Yeah.
To what extent does this work extend and inform the relative relationship of place cells to grid cells?
Yeah, so grid cells, they phase remap. They don't really they don't do a global remapping like place cells do. So their remapping is not quite as expressive, and you don't quite get these same distances in this rate space as you do with place cells. So for distinguishing multiple contexts, this is sort of a unique feature to a place cell map that you wouldn't expect to see in a grid cell map, which was actually kind of what inspired this, is because the grid cells seem very efficient for representing space, so I was kind of curious as to why also have place cells, and yeah.
Yeah, so the question was more about extrapolating that relative role. Do you guys have any leading hypotheses on what that may be doing, given the fact that you also have this grid system? Or is that just
we have a few, but
too early?
I would talk for a while if
Fair enough.
Yeah.
Thank you.
Yeah.
Okay, over here.
It seems like a lot of the work is focused on mapping the room and making profiles of that vis-a-vis the mouse. I'm really interested in what we can learn about the mouse from the mapping of the room, especially as it relates to comparison across the population of mice. And I'm thinking specifically if you looked at metrics along the lines of efficiency solving a maze or memory of a maze, and how that might be represented, or artifacts of that might be laden within the data that you're observing, such that we can actually make what you might think of as psychological profiles of the mice themselves based on the differences between the maps that are created.
Right. I haven't thought about this at all, so I don't really have an answer. And all of this actually comes from simulations. So I use experimental data to inform the distributions I use, but I don't actually profile any mice here. But yeah, sorry, I don't really have a good answer to this question.
Thanks.
Yeah.
Before we go to the next question, is the speaker for the last talk here? If so, okay, great. If you could just come up. Thanks. Let's go over here.
Thanks for the talk. I was wondering when you talked about the optimal trade-off between the basin of the field and the number of the fields, that just clicked into my head the trade-off between the noise resistance in the Hopfield networks and the capacity of the Hopfield networks. Do you think there is this relationship? Do you think it's doing the same thing, number of attractors, basin of attractors?
Yeah, so there was a work that somebody sent us, Aldo Batista, actually, who does this kind of characterization, I think, but I'm not so comfortable with it myself yet, so yeah.
Thank you for the talk. I just had a broader question about hippocampal place cells. So a lot of your analyses are focused on firing rate per neuron. I'm not sure the exact unit of time you use to measure firing rate, but does also pattern within a unit of time, is that also correlated with the function of a neuron?
So like spike rate, spiking variability and these types of things, you mean, or?
Yeah.
Yeah. So I started doing a bit of that analysis. I haven't really explored it that much, so I'm not sure. But yeah, I've done everything in a rate picture here, mostly because it simplifies a lot of things. Yeah.
Oh, thank you.
Yeah.
Okay, over here.
Hey, thanks for the nice talk. Again, about the optimality of the tuning width, I was wondering if you thought about how the energy cost might play a role here in terms of, for example, the fact that wider tuning fields might mean that there's higher activity overall in the network.
Yeah, you have less sparse codes the wider your firing fields are. We've thought about it a bit, but not enough to give a solid statement. Yeah.
Fair enough.
Yeah.
And relatedly, what about the sparsity in terms of the number of neurons active in each environment?
Right. So if you have you could imagine having infinitely wide firing fields so that each neuron is either just on or off in an environment, you lose total spatial specificity. And then your sparsity just depends on these Poisson gamma distributions for how many firing fields you expect a neuron to have in a room. So in large rooms, you would have very, very dense codes, and you wouldn't even be able to distinguish because all neurons would fire everywhere in every room. So the firing field width kind of tunes the sparsity in a sense, right? If that makes sense. Yeah. Okay. Should I?
Okay, let's go to one more question.
Oh, yeah.
Sorry, one more quick question. I'm a high school student, so sorry if this is a little stupid.
Oh,
but
no.
Have you considered the difference between a familiar room or a room that they're familiar with versus a novel room when you place them in and they have to analyze this whole new space? Is there any difference between the two of those?
Yeah, so typically in novel rooms, your place maps aren't so static. So here I've assumed your place maps aren't really changing. Yeah. Here I have assumed that your place maps aren't really changing and that they're rather static. But if you're learning a new room, your place maps are kind of learned over pretty fast timescales. And so this type of static analysis doesn't really apply so much. But we're assuming that these rooms have been learned already, and we're interested in, for learned rooms, how many can we store and what are the trade-offs there.
Right.
Yeah.
Okay. Thank you for your talk.
Yeah, yeah.
How do you mirror?